let's just kind of review, right, the top of 2.1, which we went over on Wednesday. So we have two sets. We have a set X and we have a set Y. Okay. And these sets, right, set X and set Y, they can be numbers, right, or they can just be objects of some kind. Okay. And for each little x in the set big X, the function f, right, maps that element to exactly one element in the set Y. Okay? Exactly one. Not two, not three, not four. Exactly one. Okay? So the function f maps each element in the set X to exactly one element in set Y. Okay? And so the set X we often call the input. The set Y we often call the output, right? But in more formally mathematics, the set X is called the domain, and the values of Y, right, are called the range. And we did an example on Wednesday, right, with people's names and their hometowns, right? The sets X and Y were not real numbers. Okay. Well, we could have a situation, now I'm making this up off the top of my head. Okay. So we have a set X, which is, say, the real numbers from 1 to 2, and we have a set Y, which is the real numbers from 3 to 5. Okay. And so our function f will map each real number set X, right, from 1, right, each real number from 1 to 2 to exactly one real number between 3 and 5 in set Y. Okay. So now again, I'm making this up off the top of my head. Okay. So here's the coordinate plane, and here's x equals 0, x equals 1, 2, 3 on the x-axis, 1, 2, 3, 4. I always seem to overdo it. 5 on the y-axis. And so for every value of x between 0 or between 1 and 2 on the x-axis, right? So from x equals 1 to x equals 2, right? This is going to be the domain. Right, of the set, right? That's the set X. Our function f is going to map each number from 1 to 2 to exactly one value of y. And graphically, it might look something like this. Now, it's too small to get fancy, right? So for each value of x between 1 and 2, right? So here's a value of x between 1 and 2, right? There's an exactly one value of y, right? So you remember each point on the graph, right, is an ordered pair. The first coordinate is the value of x, and the second coordinate is the value of y. And so these corresponding, notice that for values of x from 1 to 2, the corresponding values of y equal to 3 to 5. And that's the range. So graphically, right, that is the graph of a function f that maps each real number from 1 to 2 on the x-axis to a real number between 3 and 5 on the y-axis. Okay. All right. Questions on that? Okay. So now if you look at the two graphs down below, okay, we have similar situation as we do over here, right? Just by looking at the graphs, we can determine what the domain and the range is for the function. So in this first graph, I don't want to redraw it. In this first graph, okay, you can see, right, here's the x-axis, right, here's the y-axis, and on the x-axis, right, our numbers are going from -3 to 3. The y-axis are going from -3 to 3. Okay. And so we got to figure out the domain and the range for each of these. Okay. And the domain, right, is essentially, here's a graph of our function, right, from the example I made up. Right, the domain is all the x coordinates in the graph, and the range is the corresponding y coordinates. So in this graph, right, we have two segments, and so you can see in this segment of the graph, this point right here has is the ordered pair -3, -3. Okay. Keep forgetting that pencils don't show up. This is the point -3, -3, okay? And where this open circle is right here, right, that point is not on the graph, okay? Where that open circle is, that's the point -2, -2. And so you can see that for this first segment of the graph, the x coordinates start at -3 and they go up to -2, not including -2, right? So in interval notation, right, that would be -3 to -2, right, parentheses. Now for this second segment of the graph, this point right here is at -2, -1. And this, right, and then the graph is continuous until we get to this point right here. And I don't know what the y coordinate is for that point, right, but it has an x coordinate of 2, right? Because here's x equals 2, and that point's right above x equals 2 on the x-axis. So this segment of the graph, all the x coordinates go from -2 up to +2. And so the domain for this graph, okay, when you join these two intervals together, you get the interval from -3 to -2, or -3 to +2, okay? -3 to +2, okay? As this first segment, the values of x, the x coordinates go from -3 up to -2, but then they begin at -2 up here and go to +2. So when you graph those two intervals on the real number line, right, you'll see it's the continuous interval, -3 +2. Alrighty. Now the range, right, so we're doing what we did over here, okay? So now let's figure out the range, okay? Well, this point here, right, has a y coordinate of -3, and the open circle here, right, has a y coordinate of -2. So it's sort of similar to the cases with x. The y coordinates go from -3 up to -2, right? That open circle is. But then there's a jump up, right? And for this part of the graph, the y coordinates, right, begin here at -1. And they continue, right? This graph is continuous,
and they top out here, y coordinates top out here at this point. I don't know what the x coordinate is for this point, but it has a y value of 3. And so the y coordinates for this part of the graph, right, begin at -2, and they go up to +3. Or excuse me, -1. I'm sorry, I was reading wrong. -1 up to +3. And so that ends up being the range for that graph. So remember, the range is the y coordinates. In the graph. And the domain is the x coordinates in the graph. All the x coordinates. Okay. Kind of like what we did over here. The issue with this graph on the left is you have a point of discontinuity. Okay? There's a jump in the graph. Okay. Any questions on that?
How do you show like the jump in our answers?
With the in the range here, you notice it goes from -3 up to -2, and then there's a jump up to -1.
Oh, okay.
Right? It's not continuous. So the domain was the values of domain, right, were continuous from -3 to +2. But in the range, there's a because of the union, you see there's a jump from -2 to -1 in the y values, right? Because you jump in this graph, you jump from the open circle here up to the closed circle here. Okay. Okay, good question. Any other questions on this? Yes, ma'am.
Could you explain why you didn't include -2 in the domain?
It is. -2 is between -3 and +2.
But then in the range, how come we didn't write -3 to 3? How come we wrote that one separate?
Because when you're going in the range is the y values, right? So they start down here at -3 and go up to -2, right? On this part of the graph. Right. For this part of the graph, the y values start at -3 and go up to -2. And then for this part of the graph, they go from -1 up to +3. So there's no point on the graph that has a y value equal to -2 and less than -1. Okay? Between those two numbers. Okay? There's no point on the graph with a y coordinate greater than or equal to -2 but less than -1. That's why those numbers aren't in the range. Okay. Any other questions? Yes, ma'am.
What about the open circle at -2?
Okay, so that point is not on the graph.
Yeah.
This point, the closed circle, is on the graph.
Yeah.
So this open circle is located in the coordinate plane at -2, -2, right? So you might think, well, -2 is not in the domain, but it is, because the closed circle's on the graph and it has the next coordinate -2. You guys are asking good questions. Any others? Any other questions? Right. We're finding the domain and range right from the graph. Okay. All right. So let's take a look at the next graph. Okay. And again, right, the horizontal axis is the x-axis. The vertical axis is the y-axis.
And what you might want to do is, with graphing software, it's hard to get it to do everything you want. But put arrows at the end of that part of the curve, and put arrows at the end of these two parts. So that means the graph goes to the right forever, and then it goes up forever to the right of the y-axis. It goes down forever to the left of the y-axis, and it goes to the left. Okay. So the y-axis is what's called an asymptote, right? You should remember asymptotes from your high school algebra or college algebra. Okay. And so the graph doesn't cross or touch the asymptote, the vertical asymptote. So in this case, x equals 0. The vertical line x equals 0 is a vertical asymptote. All right. So to do the domain, since the graph goes to the left forever, there's no minimum value of x. So we represent the minimum value of x with minus infinity. Okay. No minimum value of x. And then the graph this part of the graph is continuous, but as we move from left to right, the graph goes down forever. It gets closer and closer to the y-axis, but it doesn't cross it. And the y-axis crosses the x-axis at x equals 0. And so the domain for this part of the function, all the x coordinates for that part of the function are from minus infinity up to 0. For every real number less than 0, there is a point on the graph with that x coordinate. Now for this part of the graph, the graph to the right of the y-axis, the graph goes up forever, gets closer and closer to the y-axis, but doesn't cross it or touch it. So there's no point on the graph where x equals 0 is an x coordinate. And then it's continuous and goes to the right forever. So there's no maximum x coordinate. So we represent no maximum x coordinate with plus infinity. So for every real number greater than 0, there is a point on the graph with that number as an x coordinate. The only real number that doesn't have that number for an x coordinate is x equals 0. Okay, the graph never touches the y-axis. All right. Any questions on the domain? Okay, now for the range, is the y coordinates. And you notice that the graph goes to the left forever here, and it goes to the right forever here. And it's flattening out as it goes to the left and to the right. It's actually flattening out below the line y equals 2 on the left and y equals 2 on the right. So y equals the horizontal line, y equals 2 is a horizontal asymptote. Remember, the range is the y coordinates in the graph, right? So looking at this segment of the graph right here on the left, since there's no minimum y coordinate, we represent that with minus infinity. And as we move up the graph, okay, the y coordinates, increase up to the number 2, but don't equal the number 2. So for this part of the graph, right, the y coordinates go from minus infinity up to 2. But they don't, there's no point on the graph that has 2 for a y coordinate. And then for this part of the graph here on the right, there's no point on the graph where y equals 2 is there's no point on the graph where 2 is a y coordinate, but for every real number greater than 2, there is a point on the graph with that real number for a y coordinate. So for this part of the graph, y coordinates are greater than 2, and there's no maximum y coordinate because it goes up forever there. And so the range is from minus infinity up to 2, and then all real numbers greater than 2. So remember, the domain is the x coordinates, and the range is the y coordinates. In the graph. Any questions on that? How to get the domain and range from a graph? All right. Well, we can also get the domain and range of a function algebraically. So at the top of page 2, okay, we have an example of a function. Right? And when we have the function given in algebraic form, it gives us a rule, right, for determining the value of the function for a given value from the domain x, right, for a given value of x. So in this case, we got f of x is equal to x squared over 3x plus 1. And so remember, x is the input, and let me write it this way. X is the input number to the function, and f of x, right, is the value of the function given a number x. Right, given a value of x, you can calculate the corresponding value of the function. Okay? Now, y values and function values are the same thing, right? We write y equals f of x. X is the input to the function, and y is the output. Right? So this is an example of an algebraic expression, right, relating the input x to the output y. Right? We can just as easily write y equals x squared over 3x plus 1, right? Because y values and function values are the same thing. Okay? Y coordinates and function values are the same thing. Okay? So we can, we're given element of the domain x, right? We can calculate the corresponding value in the range y. Okay. So to evaluate the function at x equals minus 4, right? You know, you just plug in minus 4 in for x on the right hand side, and that gives us the value of the function, or the value of y, for x equals minus 4. So when we do that, we have minus 4 squared over 3 times minus 4 plus 1. And when you do that arithmetic, you end up with minus 16 11ths. So the function f here, right, maps the function f here maps the number minus 4 in the domain x to the number minus 16 11ths in the range y. Okay, that's what the function's mapping from x to y, from set x to set y. All right, 1 over f of x, right? That's the reciprocal of f of x. So 1 over f of x is equal to 1 over x squared over 3x plus 1. And you know, right, this is an improper fraction. This is 1 divided by x squared over 3x plus 1, okay? And so we're just taking, when you divide a fraction, when you divide 1 by a fraction, you're just taking the reciprocal. Right? So 1 divided by 3/4 is equal to the reciprocal of 3/4, which is 4/3. Okay? So the reciprocal of f of x is 3x plus 1, right? The reciprocal of x squared over 3x plus 1 is 3x plus 1 over x squared. Next, we got to evaluate the function f at 1 over 3t. So in this case, right, our input is not a real number. It's an algebraic expression involving another variable, t in this case, right? So how do you evaluate the function at 1 over 3t? You just plug in 1 over 3t in for x on the right-hand side of the function. So we have 1 over 3t squared over 3 times 1 over 3t plus 1. So again, you got a complex fraction you gotta simplify, okay? All right, so here's the main numerator. We're squaring a fraction, right? When you square a fraction, right, you square the numerator over the denominator squared, right? So 1 squared is 1. And 3t squared, 3t squared is 3 squared times t squared, right? You square each of those factors. So 3t squared is 9t squared. And then in the main denominator, right, multiplying by 3 and does division by 3, right? So they cancel, and we're left with 1 over t plus 1. Now this denominator, right, you need in adding 1 over t plus 1, right, you need a common denominator, and the common denominator is t. One over t plus 1 can be written as t divided by t, right? T divided by itself is equal to 1. And now we're adding two fractions in this main denominator with the same denominator. So we can add the numerators. So we have 1 over 9t squared over 1 plus t over t. Okay. So we're dividing this fraction by this fraction, right? What's the rule? Keep the first fraction, change division to multiplication, flip the second fraction, right? Keep, switch, flip. So when we do that, right, we keep the first fraction, we change division, remember fraction bars are like division symbols. Right, so we switch from division to multiplication, and then we flip the second fraction. And now when you multiply two fractions, you multiply straight across. 1 times t is t, and then we have 9t squared times 1 plus t. And I'm not done. Jumping the gun. Because what can we do? We can factor out this t and a t down here, can't we? Right, t over t squared is the same as t over t times, right? T times t in the denominator. Those two t's cancel. And we're left with 1 over t, right? T in the denominator. So this simplifies to 1 over 9t times 1 plus t. Now we're done. Yes, ma'am.
Do you want us to distribute that or just leave it?
No, you can just leave it as is. Yeah, that probably had a lot of steps to it. Any questions on that, ladies and gentlemen? Yes?
Why, in like the middle part where it says 1 over 9t squared over 1 plus t over t,
Say that again.
the middle one,
Right here.
no, 2 over,
To the right.
yeah, that one. Why on the bottom would those two t's not cancel?
Because you're adding,
Okay,
not multiplying.
okay.
And let's see why that's the case. Okay? Instead of t, just put 5 in, number 5. Right? Well, you wanted those t's cancel, and then what would we be left with? The number 1?
Yeah.
Right? So let's put the number 5 in for t. If it doesn't work with real numbers, it's not going to work with variables. Well, 1 plus 5 is 6. 6/5 doesn't equal 1. So you can only cancel, okay, when you're doing multiplication and division. And so, up here we got t by itself. And down here, this is 9 times t squared times 1 plus t, right? You're multiplying. Okay. You can only do that, okay, when you're multiplying and dividing, not addition and subtraction. Okay. And if it doesn't, I want to emphasize, if it doesn't work with real numbers, it doesn't work with variables. Because variables are just placeholders for real numbers. That's all they are, is placeholders for real numbers. Okay. All right. Any questions? All right, so let's do the last one. F of 2a. So again, the input, right, to the function, right, involves another variable, right, the variable a in this case. And to evaluate f of 2a, I erased f of x. F of x is equal to x squared over 3x plus 1. To evaluate the function f at 2a, we just put 2a in for x. Okay?
So we're actually evaluating the function f at x equals 2a. So when we put 2a in for x, we have 2a squared over 3 times 2a plus 1. And again, right, we're squaring a product. So by the rules of exponents, this is equal to 2 squared times a squared. 2 squared is 4. Right? Just again, 2a squared is 2a times 2a. 2 times, right? So 2 squared is 4. A squared is a squared. And in the bottom here, right, you can oop. Did you see the mistake?
Yeah,
It's 3 times 2a plus 1. Those dyslexic moments. Okay? So 3 times 2 times a is 6a. And it's 6a plus 1. Can I cancel out an a in the numerator and denominator? No, because we're adding. Okay. If we weren't adding here, I could do it, but I can't do it. Okay. All right. So on page 3, we're going to learn how to find or review, right? How to find the domain of the function. Okay. But you know what? It's Friday. Let's give ourselves a little reward, right? We'll pick it up here on